and welcome to this video. So in this video we want to look at this system here. Well, significantly more complex, but not atrociously so. It's a so let's say we have our x1 and our x2, x1 and our x2. Now in this particular system, let's say that the output, now you know the transfer function is output over input. Now if I'm specifying an x1 and an x2, I have to specify what I want the output to be. So let's say that our output, so let me just write it here, that the input, as you expect, is f of t, which is the force we're supplying. And let's say our output is x1 of t. So that's what we're really interested in. It could be x2, it could be anything, but let's say we're interested in x1 of t. Now, to solve this, what we're going to do is to, again, we're going to use the sum of forces. That's all we're going to use, the sum of forces, but we won't just have one sum of forces in this particular case. So let's look at the first system. First system, what are the forces that are on the first system? You want to, it's usually convenient to draw for each of the masses, draw the mass if you want as a vertical line, and then now put all the forces that are acting on it. So let's put labels on each of these items. Let's call that K1, let's call this K2. So K1 is pushing this in, is pulling this mass in the left direction, because it's tilted to the wall. By the way, when you have these dotted lines, they tend to show that that is unmovable. So this wall is immovable. The ground is also immovable. So based on that, your K tethered to the wall, and we're saying the direction of displacement is towards the right. It means the force because of this will be towards the left. So I'll call this K1x1. Okay, K1x1 acts towards the left because the displacement is to the right. If displacement is to the right, then you have a friction that will be acting to the left also. So you will also have a D1. Now, if you don't mind, let me write it as D1x dot 1, x1 dot. Now, I'm using the dot instead of writing dx1 dt because that will be easier to write here than writing writing all the differentials. So those are two forces acting to the left. Is there any other force that will act to the left? The answer actually will be yes. There will be a force that will act to the left. Now, based on this motion, if you assume that M2 is motionless, if you assume that M2 is motionless, then if M1 is moving to the right, this force will try to push it back towards the left. So there is another force, another spring force that will act to the left on it, and that will be K2x1. It is due to displacement x1, and it is based on this spring constant K2. So K2x1 will push it towards the left as well. What else will push it towards the left? Now, this device D3 is a damper, is a viscous damper. We'll talk a little more about that, but think of that for now as if you've used a plunger before, a bicycle pump. Okay, the plunger of a bicycle pump, you know you have some resistance in there when you try to pull and push, particularly when you try to push the pump down. So that's viscous, you have viscous friction there, and that is actually why we use D for friction as well. We use a D term for friction, or FV I think in the textbook they use FV because it's viscous damping. Now this is called viscous damping. Friction, we also look at it as viscous damping. Okay, so this parameter, this item here is a viscous damper, or just a damper for short, and it will also act to the left, and it is based on this velocity. So you have D3x1 dot. Those are all the forces that act to the left. So if this device is moving with x1 to the right, then all those forces act to the left. Now, what will pull it to the right? Let's forget about this one's movement. What tries to pull it to the right to make it move? Okay, things that try to pull it to the right. If you assume M1 is not moving, if we say that M2 is moving, then M2 will try to pull M1 by means of this damper and this spring. So let's start with, say, the damper. The damper will try to pull it with D3x2 dot. Because we are saying x2 is moving, because of the motion x2, it will try to pull this device M1. And then also the spring. Your spring has a spring constant of k, and it is due to motion x2. So these two will try to put it to the right. Now, at this point, I want to mention the fact that we are able to do this because we assume that this system is a linear system, and actually generally that's a good assumption, that this system is a linear system. So we can take M1 on its own, do its analysis. We can take 2 on its own, do its analysis, and that works. So this is for mass M1. Let's draw something similar for mass M2. Let's look at the list, the forces, the list of forces that act on it. Now, one small hint: there are two forces that will act backwards on it, and both are actually exactly related to this. So this should be K2, X2. Both are exactly related to this. So on this object, what will try to pull it backwards? This damper will try to pull it backwards due to, if you assume that um, oh, sorry. I'm sorry. I said, okay, so let me take that again. I mentioned that two forces will act backwards that are dependent on this. Um, yeah, we'll come back to that thought in a moment. We'll come back to that thought in a moment. But let's just look at this mass M2. There's a motion X2, and let's look at all the forces that are acting on it. Well, one obvious force that is acting on it, first of all, let's just get the elephant out of the room, F of t. That force is pulling it to the right. Okay, we know that's good. Now, looking at just x2 alone, what are the forces pulling it back towards the left? Now, assuming that m1 is not moving, if you assume that m1 is not moving and you're just thinking about m2 that is moving towards the right, m2 is moving towards the right, you have a force that is acting to the left, pulling m2 towards the left, and that will be your d3 x2 dot, because this is moving to the right, and you now are trying to this. If you assume that this is motionless, then you have a force pulling it backwards because it's trying to resist the motion. Okay, this d3 tries to resist the motion that is going. Tries to resist the motion that is going. So you have d3 x2. And then this spring also tries to resist that motion to the right. So you have your K2, X2. Okay, and this is what I was saying is related directly to these two forces that were acting to the right. But that is not all that acts towards the left. You also have your viscous damper, that's your friction. When the box is moving to the right, you have a friction that is trying to pull it towards the left, or trying to resist the motion to the right. So it's effectively a force acting towards the left. And that's our d2 x2 dot. Okay, so you have your d2 x2 dot. Is there any other force that is acting towards the left? Oh yes, we left one more force in this m1. I'll come back to it. What else is acting towards the left? What else resists the motion resists motion to the right? So there's one more force that's acting to this left, and it's called inertia. And we forgot the inertia also on M1. Okay, so inertia, we have M2 X2 dot dot, double differential. And I'll include your M1 here, M1 X1 dot dot. That will also be resisting the motion. So we have these forces, four forces acting towards the left. Is there any extra force acting towards the right? Like we did with M1, we need to consider the case. Let's assume your M2 is stable, is stationary, and your M1 is moving to the right. If M1 is moving to the right, it will try to push M2 to the right by means of D3 and by means of K2. So you have again your D3 now dependent on your X1, okay? And you have your K2 now dependent on your X1. So D3 X1 dot and K2 X1. So these forces act to the right. So these are all the forces that are acting on this. And now we can come up with our um, two equations. Okay, we can come up with our two equations. And let's take for mass M1, just simply add up what you have over here. So you have your D3, which should we, okay, so D3 X2 dot plus K2X2 is equal to D1X1 dot plus K1X1 plus k2x1 plus d3x1 dot plus m1x1 dot dot. Okay, I mean, we could have written this minus all of that is equal to 0, but I could also write it this way. For the second equation, we have f of t plus d3x1 dot plus k2x1 is equal to d3x2 dot plus k2x2 plus d2x2 dot plus m2 x2 dot dot. Okay, so we have the second equation over here. Again, if you want, you could have the f of t on one side and everything else on the right hand side. So how do we go about solving this? Just to remember, what are we hoping to arrive at? We're hoping to arrive at a transfer function, and what is the transfer function we want? Output we specified is x1, input we specified is f of t. So we are hoping to arrive at x1 of s, all divided by f of s. This is what we want to arrive at. Now, in order to arrive at a transfer function, we need to assume, remember, assume 0 initial conditions. So we're going to assume 0 initial conditions. Typically, the problem set or the question will tell us to assume 0 initial conditions, so we don't have to specify it. However, if we're not told, then we should specify that we're assuming 0 initial conditions. So let's go ahead and just find the Laplace transforms of the first equation, for instance. So Laplace transform of the first equation, that gives us that d3. So we have an s now. S d3 x of s, x2 of s, plus k2 x of x2 of s is equal to s d1 x1 of s plus k1 x1 of s plus k2 x1 of s plus d3 s d3 x1 of s plus s squared m1 x1 of s. Now, from this expression, we can see that we can collect like terms. Let's collect like terms, and let me not jump too many steps. So we have sd3 plus k2 multiplied by x2 of s is equal to x1 of s into, let's start with the s squared term, s squared m plus s into d1. What else? We had d3, d1 plus d3. So you have d1 plus d3 plus, you have the constant terms. Well, those that don't have an s or an s to the power 0, you have k1 plus k2. Okay, so this is our first equation. Let's take the second equation. Laplace transform of the second equation tells us that f of s plus, can I skip a step here and just simply write x1 of s into s d3 plus k2 is equal to x2 of s all into s d3 plus k2 plus s d2 plus s squared m2. So this is where we're at this point. X1, remember, excuse me, X1 is our output, F is our input. So we want to get rid of this X2 if possible. If you want to get rid of X2 if possible, is that possible? I think the answer is obvious. Looking at this first expression, you can write a parameter, you can write an equation for X for X2. So from this expression over here, we have that our X2 of S is equal to X1 of S into S squared M plus S D1 plus D3 plus K1 plus K2. All of this divided by S D3 plus K2. Okay, so all of this X2 is equal to this. Now we can come back to this equation and now write it out in terms of just F and X1. So now we'll have F of S plus X of X1 of S into SD3 plus K2, and this is all equal to X2. X2, remember, is X1 multiplied by all of this. So all of this is equal to X1 of S into, and now this will be a long expression. So we have S, I'll collect like terms in here. So that'll be S into D2 plus D3 plus okay, so let me start from the S squared term so that we are just rather consistent. So we have S squared M2 squared, sorry, S squared M2 plus S into D2 plus D3 plus K2. So all of this, that's yes, plus K2. All of this now multiplied by what you have in this numerator, and everything will now be divided by what you have in this denominator. So all of that multiplied by S squared M, this should be M1, I believe. Let me just confirm that that is actually M1. I dropped the M somewhere by mistake. Yeah, that should be M1 because that comes from here, M1, okay? So that will be multiplied by S squared M1 plus S into D1 plus D3 plus K1 plus K2. All of this divided by SD3 plus K2. SD3 plus K2. So we can now pull all the X1 terms to the right and now come up with one expression that stands for the transfer function of this system. This video so far is 18 minutes long, and I think I want to stop at this point. Now, I encourage you to okay, so let me just stop at this point for a moment and then I'll continue in the next video. Thank you.